Hi, welcome everyone. So let's get started. My name is Anuj Batta. I have close to 2 decades of work experience in the IT industry. I have been working in data-based decision making since beginning of my career. We have seen a lot of evolution. We have been calling this domain with different names like business intelligence, data science. Now we are moving towards AI and ML, etc. I work for companies like Adobe, Sapient, HCL Technologies, etc. I am Calcutta alumnus, and I'm currently also pursuing a PhD in the same domain, machine learning and data science from IIT Delhi. For last 5 or 6 years, as a started as a hobby. So I started mentoring and teaching a lot of data science aspirants, and now I kind of spend more time on this because I really like it, and that's one of the ways I am able to bridge the gap between academics and the industry. Today we are going to cover random forest. So we'll talk about classification. What is it? How is it different from regression, etc. Different models which we can use. What is the concept of random forest? Why we use it? What are the advantages? What are the things which you need to take care of when you are implementing this? And of course, this is an ensemble model. So we'll talk about ensembling as well, bagging, boosting, etc. The concepts which are used for random forest. So we are going to talk about those. Then we'll give you some analogy to understand why and how we implement this. And then, of course, we'll understand step by step on how do we implement this. And then I'll show you a quick, simple demo in Python so that you also get some idea on how one of the ways to implement random forest. Let's start with the topics. Why are we talking about classification here? Even though random forest can be used for both classification and regression, which I'll talk about, but our focus would be largely on classification using a random forest. At a very high level, in data science, we primarily can do only two things, right? We can either do regression, which is predicting a point value or predicting a continuous variable, or we can put different objects or data points into groups. At a very high level, that is called classification. So these are the only two things which we can do. But if we drill down and we look at further things within grouping of different data points or objects or entities, then we can look at this classification itself as a name, which is a supervised learning algorithm. Or we can also look at clustering or association mining and things like this. But here we are talking about classification as the specific supervised learning grouping algorithm. So when we say classification, this is as good as identifying your data and putting them in some predefined classes. To understand this example with the image that we are looking at, we have different trash cans, and as human beings, we have learned how to identify different objects and how to map them into different classes. So here we can say this trash cans, which are labeled as organic, paper, glass, etc. They are different classes or different group names. So why are we calling it supervised learning? Because we know which object would belong to which class. And how do we know that? We have certain mapping done in our brain based on our historic learning. So we can identify which object belongs to which class, right? So we can easily put our waste products into the designated class. And that's what is a way of supervised learning, which we also implement in data science when we are doing classification. So here, every object which is represented here, like fish bone or banana or a empty box or things like those, are in data set that becomes our data row. If we have to relate this to our data set, so every object which we are looking here and we are trying to put that in a class is actually our data row. So when you get some data set, in that one of the column would be a data class, and all the rows individually will represent one object. So what we are going to do is, as human beings, just like we have learned, we will train some of the model which makes most sense in that context. We train that model and we tell that which row belongs to which class. Now once on a lot of data the model is trained, then we can supply with a new row without the class, and the model will be able to predict that which class this object should go into. And that's where we do classification using supervised learning. Now, as I said, regression means we are doing point value prediction. For example, somebody wants to know what can be the recession in next quarter in my company, right? So that can be a specific value like 9.5% or 10.5%. So we are talking about a continuous variable. How much sales would happen for the new product that we are launching in India, for example. So that is again a point value prediction. So that's what is regression. So if I take this simpler example, when we are trying to classify between, we are asking a question, will it be hot or cold tomorrow? So we are trying to put the data into a class, and we have just two classes. So it's a binary classification problem, hot and cold. However, as I said, in regression, we are going to predict a point value. For example, we are asking a question, what is the temperature going to be tomorrow, right? Which would obviously will be a continuous variable, whether it's Fahrenheit or Celsius or any other prediction which we do like this is our regression. As I said, there are different models for different objectives. However, there are some models which can be used for both classification and regression. And random forest is one of those algorithms which can be used for both. Now, there are, when we talk about examples of classification algorithms, so I would also like to point out that first of all, we should look at the algorithms today into three segments. And this is not from the regression or classification approach, but from overall, domain or the kind of area where which the algorithms are coming from. So we have three set of algorithms generally. First set is of your statistical algorithms, right, which are based on the statistical and mathematical equations and concepts. Then we have a different set of algorithms which are bio-inspired or biologically inspired algorithms. So you must have heard about artificial neural networks where we try to mimic the behavior of human brain, right? So that's a bio-inspired algorithm. Or we have genetic algorithms as well. Then the third set of algorithms are the nature-inspired algorithms. And there are around at least 100 plus algorithms which are nature-inspired. For example, ant colonized algorithm, cuckoo search algorithm, or frog leap algorithm, so or water ripple algorithm. So what the idea is, whatever happens in nature, for example, if you throw something in the water, there are ripples which are very, in specific shape and frequency and things like those. Or when we talk about frog leap, so we know when a frog needs to go from place A to B, it kind of leaps and or jumps. So how does it know that which is the best place for me to jump? So scientists have evolved, some algorithms based on this, and there are a lot of optimization problems that get solved due to these algorithms. Then cuckoo search again is nature inspired, where a bird cuckoo never creates its own nest. It always puts eggs or lays eggs in somebody else's bird's nest, and then it kind of naturally predicts the highest probability where the eggs would be safe and be hatched. So that's where we also try to implement that kind of natural phenomenon. And these algorithms, as I said, are widely used. So, for example, Uber, Ola uses this cuckoo search algorithm for one of the applications when they are assigning cabs, etc. So here we are talking about classification algorithm, and the kind of algorithms you look at on your screen right now. These are the statistical driven algorithms. So we can have logistic regression, decision trees, random forest, naive Bayes, etc. And of course, there are a lot more of algorithms in the list. Based on the experience, I can tell you that random forest is one of the most widely used supervised machine learning algorithm. And as I said, this is used both for classification and regression. Random forests are built on the concept of decision trees, and that's where I was saying that it's good if you know decision trees already. Decision trees are one of the simplest algorithms in terms of implementation, as well as in terms of explaining how things are working behind the scene, right? So decision trees work like a flowchart. You start from the root node where you give all your data, the training data set, and based on a lot of different parameters like entropy, Gini index, or other algorithms, it kinds of divide your data set into at least two subsets as shown here. The data is here, the main data set. Now it gets, so suppose this is a classification problem. Now we are saying the data gets divided into two sets, subsets. One is this, right? So it is subset A and this is subset B. How this data split happens? It happens on different algorithms, which I am talking about, like Gini index, entropy, variance reduction, or there are other algorithms. The primary idea is that we are trying to segment the data so that it gets purer. By purer, I mean the final objective is that all the data should belong to one class. When I have the data on the first node, and I have just two classes, false, true and false. So of course I have data mixed for both the classes. Now I'll run some mathematical functions and I will try to divide this data so that I have more purity or lesser impurity in a node, which means if there were 50 rows of my data, out of which say 25 were false, 25 were true. So this is completely impure node. I would try to bring some data where I have false data set is larger here, and maybe true data set is larger here. And I keep on doing this until I get either completely pure nodes or I have some threshold set. So that's a very high level way of understanding how decision trees work. Now, as I said, these are the most simplest form of algorithms because it's very easy to explain to a business user that what is happening. Unlike other models which you might have seen, like regression or neural networks or any other model where some mathematics is going behind the scene, which is difficult to explain to business users. But here it's very simple to implement and explain. If that is the case, if decision trees are so helpful and so easy to use, then why do we need to do something on top of decision trees? So that's what now we have to look at, like why do we need a random forest? So one disadvantage of decision tree is that it does not perform very well on the real data set. So it tends to overfit. Now, overfit is a concept where it does very well on your training data set, and it does not do well on your real data or test data, which means you have very high variance, right? It has low decision trees generally have low bias, which is they fit very well on your training data set, but they have very high variance, which means they don't do well with different data sets which they haven't seen. To overcome this problem, we still use decision trees, but in a very different form, which is called random forest. Okay, so we'll understand what happens. So there's a very beautiful concept which can help us in understanding this concept of ensemble learning. Right? So this decision tree is based on ensemble learning. So you must have read or heard this story in your school days or early childhood, the fable of blind man and elephant. So there are a bunch of men who want to know how an elephant looks like, and unfortunately all of them are blind. So what happens is they try to touch the elephant and try to know how it looks like. So the person who kind of touches the trunk, he tells everybody that the elephant is like a broad bamboo. Somebody touches the elephant from the side and he explains that the elephant looks like a wall. Somebody touches the ear and says it's like a fan. Somebody touches the tail and they say it's the elephant looks like a rope, and they keep on arguing and things like those. From this, we would understand what is ensemble learning. So what happens is when you combine the results based on votes from different entities, like it does not use just one model, it uses a lot of different models, and then uses a vote to finally identify the class or the prediction value. That kind of approach is called ensemble learning. Now, good part about this versus the story which we have seen is we can control what kind of data we are showing to different algorithms. And this is not something like completely blind people checking different areas completely of our data set. So there will be a lot of confusion. So as we'll proceed, we'll understand this in detail, that how ensemble learning helps in getting the better predictions than decision trees. But this idea is to just understand that ensemble learning means different algorithms would work on your data set in subsets of your data set, and then we'll do voting between these two. All these algorithms. So there can be like 100 different algorithms which are running under one random forest. So now we'll understand how it happens. Okay. So we will now add, so that was called ensemble learning. So this is a concept. Now what we use in ensemble learning is bagging and bootstrapping. What happens is this concept of voting itself is called bagging. Okay. You have a data set, and for simplicity, we are here taking just 4 variables. Chest pain. So somebody is trying to predict whether a person has heart disease or not based on 4 attributes: chest pain, blood circulation, some parameter, yes or no, blocked arteries, and then weight of the person. So what we do is we have a lot of data which already has been labeled, like heart disease is available. So we train the models, and then we take this data, take subset of all this data, and train multiple models on top of it. And then finally, we take vote from each model. When we pass one specific row, for example, here, suppose so there were say 1,000 data rows with these many columns. We trained 100 different decision trees or models on this data set. And finally, we ask every individual tree that what do you predict? What should come here, yes or no? And we are seeing that 95 trees predict the value to be yes for this data which we are passing. Yes, 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 and 169, right? So 95 of the trees are voting for yes, and 5 trees are voting for no. So we'll go with yes, and that's what bagging means, right? So we are running 100 parallel algorithms, and then we are aggregating the results based on the votes here. So let's see this in detail now. What happens? So you take your entire data set, create n subsets of your data. Now, interesting thing is the size of the data remains the same. So all your subsets are equal in terms of number of rows, which means you are taking subsets on random selection with replacement. And I'll explain that in the next figure. But just remember that we are creating n subsets, or n can be 100, 250, or whatever number which makes sense. So those many subsets of your data, but all of the subsets have equal number of rows as your main data set. Then what you do is you create one individual tree on each data set. Now, what is the difference between these trees? One is they are getting different data, because even though the size is same, but there would be a lot of repetition of rows, and then 2 subsets will not be same or equal to each other in terms of the data. They are same in data count, but they are not the same data. Other difference is that every tree is not exposed to all the columns. So if there were 10 columns in your data set, your subsets will also have 10 columns, for example, but the decision tree will not be supplied with 10 columns. We would decide how many columns do we want to give to every node while splitting. It can be 2, 3, 4, whatever number we think is right. And then the tree would be predicting based on different columns and different data rows. After which we are going to test, and I'll explain how do we do this process in detail, how do we create these data sets, and how do we decide how many columns and which columns to pick. But this is the general idea of bagging in random forest, right? So just to reiterate, take the entire data set, create n subsets of same size. Of course, data is different because what we are doing is random sampling with replacement. Then we pass on this data to different trees where we have different columns for the tree and which is at random. And then we are going to train these individual trees, and then we'll take the vote of these trees. As we have something called bagging, there is another concept called boosting for ensemble learning. But in boosting, we do not run parallel algorithms. We run sequential algorithms, and there are different algorithms for this. Random forest does not work on boosting, okay? It works on bagging. So in boosting, what we do is we take the data set, we train one model, we learn from this model, we change a few things, we change some data, we, wherever we have the max confidence, and there are other things which happen. Then we train the next model. Then we get the output, we learn from this, then we train another model. So even here we are using multiple algorithms and models, but we are doing that in sequence rather than in parallel. And eventually we'll have a final outcome. So this is the concept of boosting. Both bagging and boosting are ensembling algorithms. So let's now understand some analogy so that we get more clarity on this. So Chandler here, our friend, is trying to plan a 1-year vacation trip. Now he wants to choose that where should he spend his time and things like those. So he's trying to get the destination for his vacation. So what he does is he asks a few friends that where should I go. Now the friends would ask him questions like which place do you would you like to spend time, are you adventurous, do you want to go to calmer place, or things like those. So there would be a lot of questions, and I'm explaining this because that's what the tree also do with the data, right? So one friend can suggest a specific location, second friend can suggest another location, third friend would suggest something else, and of course there would be some overlap. And then the process continues. Chandler keeps on asking more friends, and eventually what happens is, after asking everybody, he sees that what is based on my interest, which place is being suggested by my friends maximum number of times, right? So it is just like voting. And that is how your random forest also works. So you provide information to different algorithms, which are friends in this analogy. And then you finally decide on the maximum number of replies, which we are calling as weights. So now quickly, what we are going to do is we'll again intuitively see. So what we are saying, we have data set. Now we are building multiple decision trees. So there will be a lot of decision trees. Here we are just showing 3. But if you have like 10 variables in your data set and few hundred rows, we can easily build say 30, 40 decision trees. As the size of data set increases and as the columns increase, you can continue to increase the decision trees. And this all will come when we do the matrix evaluation, and we see what number of trees are giving you the kind of right prediction. So that's where we decide on number of trees, but we can start from a number based on the suggestions or suggestive measures which are there. So there are no hard and fast rules, as I said, that you always start with 20 trees or 25 trees. So that's a generic question which is there when you start on this, that where do you start from. So it comes generally with practice and here it'll try, and then of course you can get some recommendations from different sources like research papers, etc. This is what looked at, but now we are saying talking about all the steps. So you have your entire data set, you have divided this data set into subsets. We have the same number of rows, but the rows are not same, right? So we don't have the same data in different sets. So we then train n number of trees. We provide this each subset to each individual tree. We have randomly selected columns for each split on a tree. Once that is done, we know the result of every tree. We then take the voting for every data point, and that's wherever we are getting the majority of votes, that's the class which we assign. So that's at a high level how we create a random forest. This is now example of creating these subsets of data. This process is called bootstrapping, the creation of subsets of data. So for example, the same variables we have, now I have 4 different rows. So what we'll do is we'll create subsets. Every subset will have 4 rows only, but we'll pick them at random, and some of the subsets would have repetition on different rows. So let's see how it looks. For example, this is one of the data sets. Okay, on the left hand side, I have the original data, and on the right hand side, I have the subset. So if you see, we have 4 rows in the subset as well. However, this row here and this row here are repeating. So this row 75 has been taken twice, which means now some tree will take these two rows only and repeat them both. Some tree might take first and fourth row and repeat the fourth row thrice. So this kind of permutation and combination will occur, and you will have n number of subsets. So this is what is called bootstrapping of your data. Now, once you have your bootstrapped data set, so this is the same data set, which this is the same subset, right, with two same rows. And this time we are training a decision tree on this data set, but we are not taking all the columns. So here we are only taking these two columns, and we hide these two columns from your decision tree. So these two columns are not shown. Now this node here will split your data based on these two columns only. And the next tree can get a different kind of, so a different set of columns, right? And that process will continue to happen until, so as it says, instead of all the four variables, we are going to take only two variables. This is your bootstrap data set. So we are taking bootstrap data set using random columns, subset of the overall columns, and then building a decision tree. Again, on the next node, we can again take a subset, which and so suppose this was partitioned on high BP. On the next node, we'll hide this column from this next node. We'll offer these three columns. And as I mentioned in the beginning, based on different algorithms like Gini index, you can read about these when you study decision trees, or entropy, or variance reduction. So automatically it will pick which is the best column out of the columns which you are exposing it to, will make your data pure. But the idea is that we are letting different nodes take different columns to do the splitting of your data. That's why most of your decision trees will be different from each other. That is the important concept to understand. So eventually what will happen? Your original data would be used through different data sets to create multiple decision trees, and all the decision trees will be different from each other. You keep on doing this until you have significant number of trees. For example, here it says ideally you should have to repeat this step hundreds of times, because we are talking about a real scenario where you have a lot of columns and lot of rows. And in a real practice, real projects, you would see there are more than 100 variables. There are hundreds of thousands of rows. There, this kind of algorithm will make a lot of sense, but then you have to create a lot of decision trees. And when I say you don't have to do all of this manually, right? You simply take a function and your function will do all of this for you, but you need to know what is going behind this, what is happening behind the scene. And then you have to change the hyperparameters. And you can only do that once you understand all of these details. The last thing is we are now going to take the votes. So this is data set, which was the same example which we looked at, which was repeating. Now what we'll do is we'll take this data row and we'll check each and every tree, whichever tree received this row in the data set, and we'll see which class that tree has predicted. So if out of 100 trees, 95 have predicted this as yes, and 5 has predicted this as no, we'll take this as yes. Now you would ask me, what if there are 50-50, or what if 60-40? How do we know, which to take? But if you think intuitively, this data set is, one of the rows from the data set. So that kind of situation will never occur. Most of your trees will be predicting it in the right class only, right? Intuitively, if you think about this, there is a significant relationship between these attributes and this class. Only there will be few trees which are have used specific set of columns due to which there is a wrong prediction. But this voting actually is the thing which gives you a very high accuracy when we use random forest, right? So you will never get into a situation where you'll get 50-50 votes for most of your data set. If that is the case, what will you do? You will change the number of trees that you're building. even though that never happens, but if you continue to face this problem, you know you are not picking the right algorithm. You would switch to some other algorithm for sure. Then the last thing which we need to understand about this is how do you test that how good your model is working. The example which we looked at, we only created one subset of data. In that, we did not pick the fourth row. Now, in real practice, when you are implementing this, you are going to notice that around 25 to 30% of your data is never picked by any trees. That data is called out of bag dataset, which means there are some of the trees which have never seen this row. Now, unlike other algorithms where you have to, do multiple iterations of training versus test split, here what you will do is you will use out of bag data set as your validation data, and you will pass this to the trees, and they will predict this value based on the learning they have done. And again, you are going to use the voting in it. And how many number of trees are predicting this class correctly would become your accuracy. So let me quickly reiterate what I said. There would be some rows which are not exposed or which are not given to the trees because of the random sampling with replacement. In the first example, we saw that that tree received only 3 rows out of 4 rows. In practice, from experience, I'm telling you that there would be around 25 to 30% of your data which will not be picked by the trees. So when we look at one tree and we see that these are the 30 rows which were not exposed to this tree, we are going to run through that tree with those rows and we'll see what that tree predicts. We are going to run through all the trees which were not exposed to those rows, and we are going to take the vote from these trees, and that becomes our prediction. Now we'll compare these predictions with our actual values, and whatever right predictions have been made, that becomes our accuracy of the model. And of course, here also you'll take care of your precision, recall, F-score, and other matrices. But for simplicity, I'm just taking example of your accuracy only. These are called out of bag data set. So it may happen that you ran it through a set of trees, and then in all you are getting like 8 yeses and 5 nos for your this specific row, and this row has been predicted wrongly because you are getting higher vote on yes. So eventually you will take this as your false positive or false negative depending on whichever class they belong to, and this will become the reason for lowered accuracy. So all these kind of cases will be part of your denominator, not the numerator, when you calculate your accuracy. But this is how we check your model accuracy. And depending on your initial confidence level, etc., if this accuracy is beyond that threshold, like maybe 90%, 95%, 99%, whatever is your threshold, then you would say that your model is working fine. Otherwise, you have to retrain or do the tuning, etc., or pick some different model. Now, if you remember, in the first example, we looked at 2 variables to split your node. You can pick between different number of variables. And when you check your accuracy, then of course, what you do is in different iterations, you do different variables. So first you'll build trees with 2 variables, you build with trees with 3 variables. Whichever set of trees is giving you better accuracy, that's the number of variables you are going to pick for your training of your trees in the next iteration. Let's now move to one quick demo. So in Python or R or SAS, for example, to achieve one task, there are always different and multiple ways. Okay, you can do the same thing with multiple functions. All of them will give you the same results because these are open source, and there are people who keep on adding different libraries and functionalities. So let's do this. I'm importing first the 3 basic libraries so that I can work on the data set. NumPy for all the algebraic applications on matrices. Pandas for deal with the data sets, like tables are converted into array-based data frames, and for matplotlib for any plotting. So we have a small data set which is again for classification. So I'll quickly show you what do we have in the data. So right, so we have a very basic data set. We have just two columns which are independent: age and estimated salary. And based on these two, we want to predict whether somebody will purchase something or not. So here we have already a label available. So this purchased is the class which can be 0 or 1. 0 might be representing that they will not buy, and 1 will show you that they will buy. I'm simply showing you only the first 5 rows of the data. Okay, if I look at the shape, for example, we have 400 rows, out of which some would be 0, some would be 1. So this is the labeled data. Because it's a supervised learning algorithm, I need to have labels so that I can train this model on this data. Okay, I basically have so let's see the info also. So here we have, for some of my rows, here it has the label as 1, right, which is the purchased class. So I have just two classes, 0 and 1. Now what I do is, in scikit-learn, I have a very nice function which is used for splitting my data set into training data and validation data. Even though we can validate on out of bag data set, which it automatically will do for finding the accuracy, but we manually also should test, and we should not expose all the data to the model, for which we are keeping 25% aside. So what it will do is, it will create the data sets, training data set for independent variables, training test data set for independent variables, then y train is for the purchased column, which is your dependent variable, and will be used with xtrain, and then test will be your hidden class values for each row in the test data, which we'll use for testing your accuracy, right? So if now I see the shape, it has taken 75% of the data from the rows. So out of 400, now I have 300 rows, and of course we already deleted or removed the column purchase. So I have 300 by 2. If I need to look at the example of sample data, so this is what we are getting for age 30. This is your salary. So this is your just 3 rows we are showing in the X text. And your training, sorry, Y will have just your predicted ones and zeros. So this is the training data set. So we are going to give this to the model. This will keep with us. And for those rows, we'll then see what your model predicts. And then we'll compare against these. Okay, that's what will tell us the accuracy. Even though your decision trees or random forest don't need a data to be scaled, but here we are scaling it for the purpose of visualization, so that we can accommodate them on axes. So we are scaling this data. By scaling, we mean we are trying to remove the unit from your data and bring them close to small values between. Generally, we are using standard scaling, which will use the standard deviation method, or z-score, if you know in statistics. So your values will primarily be between -3 and +3, and irrespective of the size of the data in units, they all will become similar in nature. For example, in the real data here, age is a 2-digit number, salary is a 5-digit number, but when we scale them, both of them will become a very small number, right? So we can easily visualize them. So there will not be a bias in the images. Now there are some models which need the data to be scaled before they can be implemented, unlike decision trees. So here we don't need to, but here we are doing it for visualization perspective. Now, as I told you, we can use different mechanisms for splitting. Here we are using entropy, and we are simply creating only 5 trees, because we have a small data set, right? We don't have to create hundreds of trees. So if you change this an estimator, you would know how changing your trees is changing your accuracy. If you change entropy to Gini or some other variable, which will be implementing the mathematics for splitting, it will also help you in terms of testing, which gives you better results. A random state is equal to 0. So within one programming language also, as I said, you might get different samples if you don't use this random state. In R also you have something called set seed, which means it always will take the same sample no matter how many times you run this algorithm. Okay, it will not make impact on your accuracy, etc., because as I explained earlier, that will be taken care of due to the large number of trees which are being generated. So this is, we have ran the random forest classifier on your data set, and we have now training the model using X train and Y train. Now, as the model is trained, so what we do is we pick any random, data from your data set, and then we scale it, and then we try to predict using this same model which you have trained, because we have put your model into a variable called classifier. So here we are saying classifier dot predict. Here we were doing classifier dot fit. So we are giving just one example. So it should predict 0 or 1 depending on whatever this random forest has predicted for this tree. So this is just to show you that if I pass any X value, it will automatically give me a Y. So now what we can do is we can go to our data set. We can see what is the actual class for this data, and then it will see if it is 0, we know it is rightly predicted. If it is 1, we know it is, if it is different, it is wrongly predicted. But we don't have to do this for each and every data row. So what we do is we take your we take the test data and we try to predict your model on all of the rows together, and we are putting that in a variable called Y prediction. And then what we'll do is we'll compare all of your actual values with your predicted values in one go. Okay, for which, so this is what we have done. So here if you see most of so here we have first we have predicted value, and second is the actual value which we got. So if you look at this one, this is wrongly predicted. So far I can't see any wrong prediction before this, and then we have more wrong predictions here, right? So this way you can actually see, if you want to look at each individual value, so which one are rightly predicted versus wrongly predicted. But if you want to do this in terms of accuracy, etc., so you can create a confusion matrix. So now you get 62 plus 29 are rightly predicted. So if you remember, out of 400 rows, we had taken out 25% for testing, which are 100 rows. So here we are getting 91% as your accuracy. So we can say that overall, out of 100, 91 are predicted correctly, because you see 3 and 6 are the wrong predictions here based on your confusion matrix. Now what we'll do is let me not visualize this. Let me rather show you actual trees so that it gives you more sense. So import pill, it's a pillow library which is for managing your images. Py.plus is again creating files, etc. from your images. Glob will be used for converting a tree into like the numbers into a visualized tree. And export graphbase is part of your scikit-learn, the tree submodule, which is used for displaying any tree or any other image. Okay, so I'll import these libraries. Now I'm creating a function called save tree as png. It will accept outcome of a model, which we have seen here. For example, so this will be the first argument to this function. Then we have iteration. For example, how many trees we want to generate. Feature name is the name of your independent variables. Here it will be age and salary, and then target, which is your purchase. So what I'll do is I'll pass these 4 values, and then I'll create a file with appending purchased and the iteration number, and then we'll add png to it. And dot data, as I said, this will be used to generate the trees. And if I run this now, it will simply create this function. And I am now extracting the feature name as the first 2 columns of your data set and target name as the last column of your data set. So it will give me these 2 variables. If I quickly test, target names has purchased. So we are good. And when you when you train your model, you put that into the classifier variable. If you want to look at your output, so you can use that with object of this class estimators underscore. So as we created 5 trees, so it is giving us 5 different tree data. If you want to look at a specific tree, the first one, this is the first tree. So what now I do is I run a loop on this length of classifier estimators, because if I change 5 to 6, I don't want to change this code every time. And I pass these 4 variables, and I call this function that I just created above. So if I run this, it will create 5 images for each individual tree, and those are created as PNG files. Now using my pillow library, I'll be able to generate these, and I have put that in variable images. So if I show you, these are the files, and to display them, I'm going to use my image function, and with loops, I will run this. So now if you see, this is the first tree which has been built, and then I have my second tree starting here. If you see, the shape and length etc of every tree will be different because they have taken this at random. Now we just had 2 variables, right? If we have more variables and data, we'll have to have like hundreds of trees, but you can do that, all of that in your this model. So if I run it with 5 trees, I'm getting 91% accuracy. Let's quickly try to, for example, change this to GD method for splitting, and we don't change anything else, for example. And then if we predict, right? So we have improved by 1%. So this is how you will keep tuning using hypermeters. You change this 5 to 10. It might not change here because we just have 2 variables. But if there are more data, larger data sets, it would make a significant difference. Okay? So that's just one basic way of training and seeing how it performs and how we can visualize the data. So I think we'll stop here. So I wish you all the best for your future learning, and thank you for attending. Bye bye.